Hi, thank you for joining. So today, yeah, sorry, yeah, today I'll be taking the session. Okay, hi, good evening to everyone. Yeah, and the Monday session will be taken by Geetika. Okay, so uh, let's start. Please, since very few of you are here, please do respond in the chat, or you can also unmute yourself when there are things because this session, this today's session is should be very interactive so that you can take a lot of things. Okay, so I think everyone might have heard of this thing, right? Like status of tigers, co-predators and prey, or basically status of tigers in India report, which recently came out, right? So what does this say? So this basically, there's this census that happens every 4 years, or the report comes every 4 years based on the data that has been going on for the 3 4 years in between. So what they do is basically they count the number of tigers, or they try to estimate the number of tigers present in India, and how the tigers are changing across different protected areas, different landscapes, and even uh, yeah, and then the range, all these things. And then simultaneously, since they use cameras for capturing the tigers, they happen to capture a lot of other animals also, like leopards, elephants, a lot of other endangered species also. So they also give the estimate for them simultaneously. Okay, so these reports have been suggesting the tiger population is increasing, and so on. Okay, and then simultaneously, this has been awarded the Guinness Book of World Records for largest such coordinated survey for animals, because it happens at such a monumental scale. If you just look at the numbers, number of tiger photographs in 2022 alone was there 97,000 photographs of tigers, of 3,080 tigers somewhat. So this is such a huge task, and this is what most of people in the field of wildlife do, of more often. And this is not just the tigers or its co-predators. Tigers is a necessary thing because tiger is our national animal. So it's a matter of both pride, and it's a both matter of both conservation also, to know how tigers are doing. Similarly, uh, there's this report that has been published recently called State of India's Birds, because you see birds everywhere. So if you're interested, you can go to this, you can just Google State of India's Birds, and then you will be able to access this report. So what they were doing is like the conservation status of majority of the species that are present across India. Maybe either it could be migratory birds, or the resident birds, or the endemic birds. They try to say what should be the conservation priority, and then how the species has been doing overall. So they use this citizen science data like eBird, and GBIF data to to try to inform how the species are doing in this current situation. So so this is how you inform conservative decisions, or take conservation related decisions. So these are all are possible because we are doing something called population assessment of species, of like either it could be tiger, or it could be a multi-species, or so on. Okay, since just saying what are the needs. So one of the main tasks is defining the current state of a population, like how the population is doing. Like for instance, tigers. We earlier we had no idea after a time to how different populations in different landscapes are doing. But since since a coordinated survey that has been happening across You know each individual population statuses, how the population, whether it is increasing or is it decreasing, or is it stable, or it just not, there is no tigers there at all in some areas. So you will get to know from this population assessment. And then what to do with this population estimate, or understanding the state. You can either predict the future, like what is going to happen to the species, like in the next 20 years. Is it going to survive, or is it going to go extinct, and so on. And in case, if it's going to survive or increase, good and good. Like it's going to, it's if it's stable, it's good. But if it's going to increase or decrease depending on the species, we need to put management related decisions by identifying the threats to the species persistence. Or is it like, if poaching is a threat that is reducing the numbers of tigers in a specific area, you need to address those concerns, saying that you have to take decisions to reduce the poaching threats for those species in that area. So individual management related decisions help to reduce the threats, and then thereby bringing up the population. Or for instance, if it is invasive species like lantana, okay, which has been increasing pretty much in most of the tiger reserves, especially the recent assessment has found. So you need to try to identify what all the threats that this species is posing, and then how it will be in the future, to be able to mitigate the try and mitigate the impacts that it has on different other species also. So these are one of the some of the basic or the main goals, and there are many multiple goals of doing population assessments. uh, yeah. And then simultaneously, yeah, they are saying to identify and then implement solution that that ensure the persistence of the species in the longer term. Or if it's a invasive species, try to remove it from the system. Or like for example, for the persistence, like recently, if in Tamil Nadu, this year only, they have established uh, a protected area for slender loris, which is endemic to the southern India. So this has been this has been advised by population estimates assessments of the species in that area. Okay, so when you do population assessment, you do a lot of things, but mostly you talk in terms of population size, or population density. uh, okay, so can someone say what is the difference? Is there a difference between population size and density, or both are the same? Can someone comment? What do you think? What do you guys think is population size and population density? Or these two terms different, or they convey the same thing? Feel free to unmute, or you can drop your answers in the comment section or messages. Population size is the number of individuals in the population. Okay, someone said different terms. Someone is asking a question which I will come to answer. So there are different terms, and then someone defined population size as the number of individuals in a population. Okay, what about density? What do you guys think about density? So since someone Rajeshri pointed out, these are different terms. Yes, absolutely, these are different terms calculated from a single thing. Density is the population per unit area, and population is only number. Yes, yes, you guys are absolutely right. Rajeshri, you're saying population in living in per square kilometers. So you can better say it as per unit area, because the unit area can be a square kilometer, can be 100 meters, can be a meter, depending on the species and the area that you're looking at. So it's better to say per unit area. But if you're specifying the species, you can have it as per square kilometers or per 100 square kilometers. Okay. So yeah, these are in different terms. So let's go for size. It's basically, as you said, is the total number of individuals in a population. For example, if you see this, this plot or the image, if you count the total number of individuals, let's say this as a population of some species, whatever species you want it to be. If you count, like, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19 to, you know, uh, 38. The population of this area, of the species in this area is, 38. But density, or the total number of individuals per unit area. Per unit area, let's say for example, our unit area is defined by this one, one cell here. So how many cells we have here? One, 2, 3, 4, 5, 6, 7 plus 18. Sorry, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, 26 cells we have. And then how many individuals we have? 38. So the density will be 38 by 26. So so that will be the whatever the value it gives. Can someone quickly do the calculation? 20, 38 divided by 26. It's somewhere around 1.46. Okay, so so that will be, the density. The total number of individuals is 38, and the density of the population is 1.46 per cell, which is a unit which we are defining as here. Okay, so just don't get confused between these two terms, and they convey different meanings. Okay, uh, and then density is a better term. It helps you compare across different areas when you have, standard like per unit area. When your unit area is cells, or let's say per square kilometer, you are trying to count how many cheetahs are there in a protected area from, central India like Kanha, to a protected area from Gangetic Plains like Rajaji Tiger Reserve. So if you're trying to say, let's say Kanha has, 30 individuals of cheetal per square kilometers, and Rajaji has 40 individuals. So you know that, Rajaji has higher density of cheetals per square kilometer. However, if you're trying to say per size, it is just the size, population size, it might not be in a valid comparison unless you are saying what is the area that cheetals are staying. So density is a better way to compare across, but sometimes size might be a better option. Okay, so since we are just say, how do we count species? So one thing that we just found out, or we just did was discuss was, we can count each and every individual present in an area, right? So that's the way we everyone do try to do at least. But do you guys think, is it possible to count each and every individual present? Let's say for example, you go, let's go back to the tigers as example. Can you go and individually count each and every tiger present, in a particular area? What do you guys think? Yes or no? Or let's reduce, or not across the India, let's reduce the area, let's say in the state of Madhya Pradesh. Can we go and count all the tigers present there? Is it possible? No, no. Do anybody like to differ from this, or is there anyone who says yes? Feel free to, argue here. Okay, so most of you think it's no, but I will say yes, because the tigers are, where are the tigers found, at least currently? Mostly in the protected areas. You go to a protected area, since they are very few in number, it might be possible, to do it. But I'm not saying it's surely yes. It depends on the on the, what kind of resources you have, the time, the number of people who are willing to do it. But as you guys have said, it's mostly no for most of the species. Like say, if you want to do it for cow cheetal, the number of cheetal present in the whole Madhya Pradesh, it's, it's not possible. You know, not that easy to count each and every individual. So what you do? So in those cases, you you do this thing called sampling. You sample from a specific area, and then there are different methods you sample, where you sample, and then you try to use that thing to extrapolate for the different areas, the remaining part of areas. So there are multiple ways you can do. You can do what is called quadrant based sampling. You can have capture recapture sampling, and so on. So for example, if I want to come back to this example, if you want to count all the species, all the individuals of this particular species in this whole area, since there are very few in number, you can just simply go and you can visually count here. But if there are so many, what you can do is you can select some of these quadrants. Let's say for 1 2 3 4 5, it's like I selected 5, each has 2, so the population density is 2 per unit area. So if I just say okay, for the whole area, it can be something like this. Okay, and then I'm sampling not the whole entire area, but I'm sampling a subset, which I'm calling quadrant. So mark recapture method, you capture, mark the individual and try to recapture and see how many individuals you captured, and you try to extrapolate it to the total, what could be the total number of individuals based on how many individuals you capture again, which I will come back into the later. And then removal methods, which is something you go hunt the animals, kill the animals, collect them, and then see how many individuals you have collected for a specific time across years, and see how the species is doing. But this method is generally not practiced in Indian context, because most of all of the species are protected under Wildlife Protection Act of India. So this is an invasive method, what we call, because it leads to the death or injury of the animal. So mostly we do is either you do a total count, or you use sampling based methods to count species. And there are many more methods. I will be discussing some of the major ones, or the ones commonly used. Okay. uh yeah, sampling. So since I was saying earlier, a sampling unit here, going back to the same example, sampling unit is, since we have divided the whole area into quadrants. Each quadrant, like the one highlighted here, can be considered as one your sampling unit. Okay. And sample is a representative subset of population. If you think this as the whole population, you're sampling like 5 to 6 of these quadrants, and that will be your sample. And then that should be representing your whole population present in that area. Okay, so that's what we refer to a sample as. And sampling intensity, it talks about how well have you sampled the entire area, or basically, yeah, it kinds of points out if you're just in this whole 26 quadrants which you have counted earlier. If you just sample two quadrants, 2 out of 26 is very tiny, so your sampling intensity can be said as very small. But if you sampled 13, if it's like a half, it's much more higher than 2. Or if it's 25, yeah, then the sampling intensity is pretty high, because you sampled most of the area of that area. So these are some of the things that are considered when you're trying to sample for for studying the populations. uh, okay. Someone Okay, do you want me to explain this answer now, or will you wait for later and then finish a little bit of this sampling concept and then go back to your answer? Okay, let me just finish the sampling, and then yeah, I will come back to this later. So yeah, those are the things, important things in sampling. Okay, and as I was saying, there are multiple ways you can sample. Whether it could be, first thing is simple random. The name only says, you go. It's so simple. You randomly select, let's say for example, for the time being we are sampling using using quadrants. Okay, let's say this is the yellow region is the region of our interest, and we have quadrants of some specified area, let's say 1 square kilometer, 1 kilometer, and then 1 kilometer, forming square of 1 square kilometer. And then you go and then randomly sample in those quadrants for the presence of a species, let's say tiger. You since as I was saying, pointing out how they use camera traps for tiger monitoring. You go there, you keep camera trap in those quadrants. So you're trying to sample the species presence in that quadrant. So here you go simply and then you randomly put it. How to do randomly? So there are multiple ways. Either you can have a random number generator, there are multiple softwares that do that, or you can use other ways of randomizing it. So randomly choose what you just number them 1, 2, 3, 4, 5, 6, 7, 8, and then choose a random number. Whatever number you get, you go and sample in that quadrant. And the next one is systematic. Let's say I go and I will sample the every second quadrant. Let's say one, two, three, uh, four, one, and then second quadrant. Every line, second quadrant. I'm sampling every second quadrant that I'm encountering. Or if you are just walking, I will walk every 10 steps, and then I will sample on the every 10th step. So it's systematic. It just goes on. But your starting point can be random, has to be random, and sometimes it can differ. But the concept is you sample every specific unit time or unit area. For here we are sampling every second quadrant. Okay, and there is another thing called stratified random sampling. If you see here, there are two different regions. The one shaded in yellow, and the one shaded in the other another shade of orange yellow. So what they depict might be different areas. Either it could be core area and buffer area, or it could be a little hilly region and then plains region. And if you're trying to sample species, because the regions are themselves are different, your estimates might be different. So it's suggested sample those two regions as two different units separately, rather than sampling all of them together. Like randomly choose 8 quadrants in the plains region and 8 in the hilly region, and then get an estimate separate for hilly region. This is the density of the species, and non-hilly region or plains, this is the density of the species. Because these habitat itself might be changing, and then that will inherently change the species density. Okay, so these are some of the major ways that you can do sampling or choosing to sample. Okay, so hope things were clear till here. How do we do sampling, and then different types of major types of sampling, and there are few more that are discussed in the video, but I felt like these are the ones that are commonly used, and then try to go over them. Okay, if you have any questions or clarification still here, just point out before moving ahead. uh, in the meantime, let me just see that assignment date has ended, right? Or is the assignment still due? Anish, can you please let me know that? Because I can't discuss an assignment which is due. I can discuss those answers once it is done, or the due date is done. Just give me a minute so that I can check it, because but I can help you understand the question a little better. So this is week 4 assignment, right? Fourth week, yes. Let me just. Okay, the solution is also out. So that means the assignment due date should have been done. Yes. Okay. Uh, okay. Sure. Let me just come back to this. So, stratified random sampling. Yeah, just give me a minute. I'll share the screen and then start it again. Okay. So, stratified random sampling. So, what you do is, so there are two different regions, let's say two different, entirely different habitats, okay, which are very different. So, inherently, they make a difference in the population as population sizes. Okay. Let's say, for example, uh, yeah, let's go back to some cheetal example itself, or sambar. The number of sambars that you see. Let's go with this thing that sambar is a more of a species that is seen in plains, but it will go a little bit high up into the hills. I mean, this might not be true for the time being. We are saying it's more of a plain species. It will stay in the plains, but it will not go into hilly areas. But there is a protected area that has both hills shown in, let's say, in the golden color, and then the yellow color represents the plains region. And then you want to have an estimate of sambars in this area, in this whole protected area. So the best strategy that you can follow in these cases is, uh, divide the hilly region and the plains region separately and sample them separately. And then you can have a equal amount of sampling across these two areas. Let's say equal amount of effort is like the number of samples you have, or basically here the number of quadrats you sample. Okay, so that you have similar sampling effort, and then the whatever the result that you come at the end are indeed what the true population is represented. Let's say hilly region might have lesser density. Okay. Let's say, for example, let me just try to write a little bit here. So if you see, let's say what we got in hilly region was two individuals per square kilometers. Okay. Apologies for the bad handwriting here. Okay. And then, for example, in plains we got somewhere around 8 individuals per square kilometers. Okay. Okay, each unit for if when you assume is a square kilometer, this each quadrant. Okay, but if you do it for all of it together, the density estimate might be uh, could be low. Let's say, for example, it can be somewhere around 4 to 5 square kilometers, which might not be true, because some areas you are seeing relatively high densities in the plains, and then very low densities in the hilly regions. Okay, so it's advisable in these type of scenarios. It's generally what people do is you divide those two areas into separate way, and then sample in a with similar effort, and then whatever the densities you get, you report them individually, saying that this is the density for this region, and then this is the density for this region. Okay. Hope that was clear. Yes, great. Okay, let me go to this question. Anish has asked. Consider the food chain: grass to grasshopper to frog, snake, and to hawk. Okay, there are four options that we have. Like, more number of hawks than grasshopper can be supported. Okay, more number of grasshoppers than hawk can be supported. Equal number of hawks than grasshoppers can be supported. None of these. Could you please explain what should be the answer? Okay. Uh, Before I explain, Anish, you yourself, can you say what do you think it is? I mean, I will explain. If you have any guesses, do guess, and then I can help you think whether you're in the right direction, or if you are in the wrong direction, I can point you in the right way. Was none of these. Okay, so you were, just give me a minute. I will open that presentation and then show help you understand it a little better. So if you, it's basically it's talking about pyramid of numbers, right? If you remember from the pyramid of numbers, the base is larger for most of these food chains, especially grazing food chains. The base of the pyramid is larger, and as you go to the top of the food chain or across the trophic levels, the higher trophic levels, it just gets pointy, suggesting what that the number of individuals in the topmost trophic levels are very few in number. Okay, uh, yes, just a minute, let me just share that pyramid of numbers, and then I can help you. Yeah. Yes. So I think you can see the screen now. So as you grow from you know from producers to top level consumers, and in a pyramid chain that is seen in most of these grazing food chains, the pyramid gets pointy, and then the number of individuals tends to reduce. Okay, so this is a grass is there, so it's a grazing food chain obviously. So there are four different trophic levels. Okay, let me just write it here: grass, and then we have uh, grasshopper, let's say GH, we have G, and then we have a frog. Okay, I think I had this example. Let me just go back here. Okay, you can see this example, right? Grass, grasshopper, frog, snake, and then let's say this is, assume it's an hawk. Okay, so what happens is the pyramid of numbers gets pointy, right? That's what we should be remembering. Okay, so what of each of these statements are saying? So first statement says more number of hawks than grasshoppers can be supported. So according to pyramid of numbers, hawks are less in number. So but the statement says more number of hawks than grasshoppers, which are obviously very much high in number, can be supported, which is not a valid statement according to this law. So it can't be A. More number of grasshoppers than hawk can be supported. So what I is saying is there is more number of grasshoppers that can be supported than hawks. Okay, which is a truth statement according to this pyramid of numbers. And let's check out other options. None of these is not a option at all. Or equal number of hawks than grasshoppers can be supported. So equal number is also not a possibility. So the answer should be or is there more number of grasshoppers that can be supported rather than the hawks. Basically, the closer or the bottommost you are in the pyramid, the greater your numbers are than the farther away from you are from the plants or the producers. Okay, especially in these grazing food chains. And there are other food chains that are inverted, like parasite food chains that are inverted. But since this is a grazing food chain, the predators are found in very less numbers, and then the herbivores or the primary consumers, here the grasshopper being the primary consumer in the example, are present in huge numbers. Hope that was clarifying enough. Yes. Okay, great. Yeah, you're welcome. Glad I could help you with that. Okay, let me go back to mark recapture. So since I was just saying, I will. So there are multiple methods that we use for assessing population sizes or estimating population parameters. One such And useful thing is mark recapture or capture mark recapture. It can be said in multiple ways because you know you eventually capture an animal, mark an animal, and then try to recapture. Once these three events are done, you try to estimate the population size. Okay. uh, let's try to solve how it is done. Okay, the basic model. And then, yeah, let's take this example. Like there is a pond, okay, which has fishes of a single species. We are concerned about single species. Let's say for example, you are working on marshir, some marshir that is which is a conservation priority species. Let's say golden marshir in an area. Okay, it, golden marshir doesn't live in a pond though. It's the rivers. So let's think it's part of a river that you're working, and then trying to understand the population. What's the population size of the species in that river? So you had to estimate. So you can't individually capture each of the species, right? Or can we do can you put camera trap and try to record them? It's not possible, right? Because it's an underwater species, and then it's you don't know where all these species, how the species move. And even if you know, they don't have any markings on them, so that like the way you identify tigers individually, you can't do that thing, same thing for the species. Okay, so what to do? So we can do this capture mark recapture technique on them. And then how do we estimate? So there is this formula. It's the simplest way. uh, it uses the law of proportions. So basically it talks about, let's say, initially you capture 10 individuals out of an 100 individual population. So again, when you capture 10, if you happen to capture 10 more individuals, the population is also 100 individuals. So it's trying to use somewhat proportions to calculate, but the simplest form, the formula in the end becomes something like this: n is equal to m into c by r. So n is the number of population individuals in the population, which is obviously we are trying to measure. M and c are the number of individuals captured and marked in the first attempt. Since I was saying there is this thing, you capture, you mark them, and then release them. So number of individuals that were captured and then subsequently marked in the first catch. You multiply that value with number of individuals captured in the second time. So you are just trying to multiply the number of individuals caught in the first time and the second time. Because second time you might find some marked individuals also and unmarked individuals also, divided by the number of recaptured individuals. So recaptured individuals are those individuals that you captured in the first time, and then you put some mark on it, and then you recaptured it. So let's say for example, let's go to the example of the fish. Okay, golden marshal which we are discussing. There's this river, and then these fishes are living happily. So one day I decide, you know, let me go and find out how many species individuals are there in this population. So I go, I can fish for them using a hook, or I can use like say nets to catch them. And then after spending a lot of time, I end up catching six golden marshes, which are the ones that I caught. And then I can tag them. I had to mark them, right, to know that these are the individuals that I have caught. So how do I mark them? Either I can, there are multiple methods depending on species. I can have a small radio transmitter with a chip with a tag, so that whenever I scan it, if the chip is there, it will tell me what's the number or the what is that individual, whether it is captured or not. Or I can make a visual marking, like I can you know clip put a clip or color tag on it, on its fins or on its body, saying that you are marked. And then once this marking is done, and then you know I will release the fish back into the river. And let's say after a year I go back again, and then does the same thing with the same sampling effort. Basically, let's say for example here I sampled for 2 hours and I got six individuals. So next time also when I go for 2 months or 1 year, whatever the time period is, I do the same thing sampling, and then for the same duration, since I earlier done for 2 hours, I will do it again for 2 years, 2 hours, sorry. So once I collected, so this time again also I end up catching just 6 ones, out of which two individuals were the ones that I happened to mark. Four of them were not marked at all, because and I'm capturing them for the first time. And then now I have the data, and then once these things are done, I will release. I release them back, and then I came back and I wanted to what's the population? What's the population? Okay. So what I will do is I will go back to this formula and plug in those details. Okay. Uh, so can you guys help me solve this thing, and then estimate? Let's estimate the population. What's the population size of the fishes in this area? So if you remember what is M, I'll just write down. So please you do the calculations and then report the values in the text chat box. Okay. M is 6, the number of individuals that are captured during the first term, and then all of them have to be marked. Okay. And then what is C? C is the total number of individuals that you caught in your subsequent attempt, which is also 6, right? And yes, what is R? R is called recapture rate, or basically the number of individuals that you have recaptured again in the second attempt, so which is 2. So when you plug in those details, what is it that you are getting? 6 into 6 is, okay, you guys do it. I will I'll just wait for you to tell me the answer. 18. uh do any others think of any other answers, or are you getting similar values? Okay, since two of you guys said it's 18, it has to be right? So yeah, the population in that area we calculate as 18. Yeah, if you even count it's 18, just I just left 18 individuals for representation, but this is how you do it. So this is one of the simplest, okay, simplest way of doing capture mark recapture. So the thing how it's done in tigers is also something similar. You have multiple capturing stations. You do it, you capture them again, try to get multiple photos, and then how many times it has captured versus how many times it has gone, or the number of places it has been captured. They somehow use that thing. Okay, so we got to know that this area has 18 golden marshes. But do we think so there are some assumptions based with this model, which I think you guys should be able to point out, like should be able to think why some of those assumptions might not be really true. Like my first assumption with mark recapture is the population is closed. Like between the first time I went and captured, marked them, second time I went and recaptured them, the population is close between these two times. So basically, that means there have no births happening, or the deaths happening, immigration, emigration. The population is just constant. Do you guys think this is possible? Even if you go on next day, will the population still be closed in nature? What do you guys think? No, yeah, right? So this is a fundamental assumption we have with the population, that it doesn't change. Okay, so this is one of drawbacks of this model, but this has been helping. And then individuals are captured randomly, which in most cases we don't know whether the individuals are captured randomly or not, because if you think of the same example, if you say there is a uh, there is a rock here, where you can sit and sample, but there is huge steep hill, and then there is no place for you to stand and fish, and then your fishing rod or the net goes still here. Some of the fishes that are here, might not you're not be able to capture them. So so all of these individuals are not sampled equally and or basically randomly, or because you are only capturing specific subset of them, right? It has to be done randomly. And the third thing is marks are not lost in individuals. Once you mark them, you are sure that the mark will stay till you capture the second individual. If they come with their own birthmarks, that's beautiful because that makes your job much more easier for you to not even catch and handle them. Just photograph them, go again, look for the same marks. Or the marking doesn't affect survival. So if for example, in this Mashir example itself, you have uh, you know uh, put a tag, let's say bright yellow color tag, and then its predator is seeing those tags easily and then is preying on them pretty much. So its survival is decreasing, which should not happen because the assumption population is closed is violated because of this. And then there is this thing called marking does not affect recapture probability. So basically, if an animal that you captured, it gets traumatized because of animal's behavior itself, it will not try to come to that area or try to be captured again. Or for example, or if you're trying to catch mice by uh, rodents by putting them in by like the way you capture mice in the house, there is this traps where yeah, sorry. Huh. So marking should not affect survival uh, recapture probability. Basically, it should not reduce the ability of the animal to be captured. And then, or like for example, if you're capturing rodents in a forest, you might bait them with cheese or tomatoes, which they got really fond of, and then you are happening to capture the same individual multiple times because they are liking the tomatoes and they're simply coming in because they are getting free food. So that should not be happening. Okay, but there are recent there are advances that have been happening where the assumptions, if they are violated, still you can use those models to estimate the population sizes. Okay, uh, so some of the animals, can you guys think of some of the animals where mark recapture is relatively easy, where you guys can just photograph them and then try to do this rather than individually sit and capture them, mark them, like animals that are in India. Tiger, leopard, yes, any more? Elephant, lion. Okay, Rajeshri, can you explain how do you do it for elephant and lion? Tiger and leopard we know because they are this pattern, but how do you think they do it for elephant and lion? Because I personally don't remember seeing any patterns on elephant and lions. Or anybody knows any more birds? Like what do you see in birds to do this? So where you don't have to mark the individuals separately. That's what I was asking. So it's possible in a lot of other organisms, but my question here was where you don't have to mark them individually, where they it's easy for you to identify different individuals. So as I was saying, elephant and lion we can also do that. So tiger, hyena, there is a species of hyena in India called striped hyena. Crocodilians, especially by you can look at the scales or you can mark them individual scale patterns on the tail. Lion, elephants, So lines you can use, there have been studies that have used the whisker row patterns to differentiate individual lines. But for that, high close-up photos of the face for lines. And cheetal is obviously spots, wherever the spots are there, they are uniquely placed across the body in most of the animals. And in elephants, you can have marks like, uh, it's not birthmarks, but these are the marks that are acquired in the life of the elephant. Like, some of them have cut ears, or scars in specific locations, or broken, canine tooths. It's basically tusks, or some markings, or cut tails, or a lot of these things. But the thing about that, though, using those type of markings is, sometimes, let's say for example, as you're talking about tusks, there's one elephant that used to stay, which has broken its left tusk, so it has one full right tusk and then little bit of left tusk. But in all of a sudden, you see another elephant with the same pattern because it has lost its tusk while fighting. So you might wrongly identify the elephant if you don't know. These are the things. These are the different individuals. Okay, and similarly, this can be done in common leopard, snow leopard, clouded leopard, because these species have individual markings. Okay, so yeah, that's about capture, mark, recapture. If you have anything about these, do if you want me to repeat any of these or any doubts, you let me know. Okay, so moving on to it, moving on a little further. So what we have is, a lot of people, a lot of you might have heard of it, is called something called a line transect. So we call it a line transect basically because it's a straight line. Mostly you walk in a straight line, but if there's a tree ahead of you, obviously don't climb onto the tree and go ahead. You just try to go back and then join the straight line again. If there's a tree here, just go back but you try to maintain the same straight line. Okay, so these are mostly used for counting ungulates, or basically ungulates are you can cheetal sambar or so and so. Or you can use it for birds, you can use it for plants, and or you can use it for a number of organisms. But majorly it's used for herbivores. Yeah. So what do we do in line transect? So basically, you try to walk in a straight line, and as you walk on, let's say you are starting from left to right, you notice and note down the number of individuals you are seeing or heard in terms of birds. If you hear a call, which side you are seeing, and then if it's in a straight line, you use a rangefinder to estimate the distance between you and the animals. Or if it's a group, try to estimate the distance to the center and write it down, which direction you have seen it, and then the distance you have seen. And then if you have seen it in some angle, or if the same group you have seen it somewhere here, so you note down the angle so you know that it was here that you have seen that. And then you get the distance, or the parallel perpendicular distance, you get it later when you have seen it diagonal. And sometimes you can see just on the line transect itself, you can spot. Basically, you try to try and count each and every individual that you spot across as you walk on the line. Okay, so when do we do line transects? You generally try to do early in the mornings because that's the time most of these ungulates are active, or whatever the time period the species that you're targeting are mostly active. If you're doing a transit for raptorial birds like vultures, eagles, kites, you have to do when the temperatures are a little higher, like somewhere around 11 to 2, sometime around that, where the activity is much more higher. But if you're doing it for smaller birds or ungulates, you tend to do it early in the morning because that's the time they are most active, or it could be evening also. And there is always chance that some are very good at hiding that you don't see. If you don't see, you just don't see. So you try to use these numbers and the distances, to say the density So once you get this, you do something called distance based sampling. You find out the distances that you have seen, and then the effective distance is like say 20 meters in in that area where you sample, and then you estimate the total number of species that you have seen in this 2 kilometer stretch into 20 meters. Let's say it came out to somewhere around 1 square kilometer or 1.5 square kilometer. Then you call it, this is the density of this species in this area. So that's how you do line transits. And similarly, you can also do point counts. Point counts are basically nothing, but you go to a point, simply stand there or sample in that point. If you are sampling, uh, sorry guys, I'm really sorry for this patchy connection. So I was saying about point counts. So in point counts, it's used for birds also, but you can use it for plants, or used for different taxa. Depending on your question or what you're trying to answer or understand about. So in point count, you go to a point which is basically chosen randomly and try to sample, or sample for this much area or this much time. For example, you are counting birds. You go, let's say, 50, every 15 minutes I will count what are birds I see or here in that at that specific point, and then I move on to the another point. I move on to another point, and then I have the estimates for this much area, and then I can use that to extrapolate to the whole area later on. So it's not much different from line transit, but this is circular point counts. And these are majorly used for uh, vertebrates. So what about insects? Okay, at insects there are special methods that you use for insects. So one of the best method you use for flying insects is pan traps. You don't get butterflies in them because mostly butterflies, they can, once they come here they go off. So pan traps is for smaller flying insects like bees, uh, flies, mosquitoes, wasps, or aphids, all these things. So basically, what is a pan trap? Pan trap is nothing but a colored plate. It can be a blue plate, it can be yellow plate, it can be white plate, depending on the color. You just, and then you pour water or alcohol. If you're just leaving with water, you add little bit of detergent or basically surf, so that the surface tension of water is reduced, and whatever insect falls into the water gets drowned. And then you sample, the what all the species are present in that area. Okay, it's majorly used for flying insects. And then there is another method called Malay trap, basically, or flight interceptor trap. So you have a frame with a plastic sheet, and then whatever hits that sheet will immediately fall down into a preserving liquid, so which you can collect. So you can sample flying insects in that manner also. And then the third one is obviously a sweep net, which you might have seen as butterfly net. And then what about the ones that don't fly, or the ones that goes along the ground? It can be insects or smaller mammals also. So what you do is something called a pitfall trap. So here, if you can see, this is a pitfall trap, basically a juice glass size paper cup filled with surf excel water. So as an ant walks around, it's is as insects walk around, they might just fall down. If an ant, see, if you can see here, there's an ant that is walking around. So if it slips and falls down, you are getting that ant into your sampling. Okay, so pitfall trap is a passive method of sampling because you don't have to be there. You just dig it, keep it level with the ground, pour alcohol or surf excel water or surf water. So and then next day you go and collect whatever insects you have got. Sometimes you not only just get insects, sometimes you get reptiles, sometimes you get mammals. So it depends on what you're trying to target. If you're trying to capture, rodents, your pitfall will not be, smaller paper cup. It has to be smaller buckets, because rodents are little bigger and they should not escape. And then depending on whether you are willing to kill the animal or not, if you are not willing to kill the animal, if you're trying to capture, some endangered animals like shrews or something, so you keep the pitfall empty and then you come and check, every 10-15 minutes. But if you are looking at insects, you might need to keep them, in water, because they might start eating each other. So it depends on what you are planning to do. Or you can have visual encounter surveys. Here you search a defined area for all the insects that you get, and then collect them. You manually sieve them, you search whatever that moves, and then you collect them. It's called leaf litter extraction. So there are, or you can just manually check, or you can sieve and check. There are multiple ways you can do it for insects. Uh, so these are some methods that are, used for both vertebrates and invertebrates, mostly in terrestrial places. And marine habitat also, you can have something called line transects and point transect, depending upon areas. Okay, and moving on to population growth. Okay, so till here, at least the methods how we sample animals was clear, right? If you have anything, do let me know so that I can go back and clear it. If not, I will go ahead with population growth. So, guys, do answer. What do you think are the factors that affect populations, or things that increase populations or decrease populations? Any idea or opinions on, what are the things that affect populations, or population growth, diseases, food source, starting population? Yes, but if you try to put them in a different categories, what are the major categories? What does diseases lead to? What do diseases do to population? They decrease the population size, right? By, you know leading to deaths of the individuals, right? So so major things, you can classify what are things we have been saying into these categories. Majorly are births, which add individuals into the population. Deaths, which eventually removes the individuals from the population. Immigration is, different individuals from different places come, and immigration is individuals from this population leaves on to, find out different places. So different ways, uh, the population either grows or decreases or remains stable. Okay. uh, so there are different ways the population can grow, right? So if you think of a bacterial cell, where you start inoculated, you took a petri dish and inoculated single bacterial cell in the center, and then try to, let's say the bacteria, multiplies every 10 minutes, and then you want to see the total number of bacterial cells after, 4 or 5 hours. So what will the number be? So you need to understand how the bacteria, to find out that, you need to understand how the bacteria grows. Okay. Let's say what do these microbes or the bacteria display in the initial part of the growth is something called exponential growth. I'm extremely sorry for this graph. Just ignore this part. Okay, I will show. Okay, let me just go back and try to, do that graph now. So what is called an exponential growth? Okay, before we go, uh, let me just do it again. Okay. Uh, what do you guys, as I was saying here, let me just write down how to, how do we find out population has changed? As we have seen here, population at n plus 1, or basically after a while, how to find out what the number of individuals present in area. After, every 1 year you go and sample. So how do we say? It can be said as n, which was, starting population, that the other population that was observed at the previous year, plus because births add, to the populations, the number of births, and then deaths remove individuals from the population, immigration adds individuals into the population, the I, and then emigration removes individuals from the population. Okay, right? But let's say, see, in the bacterial example, you for sure know that immigration and emigration are something that's not going to happen, because you are putting them in a culture dish where, there is no nearby bacteria. You take care that there is no nearby bacteria is coming. So what are the things now affects the population are basically births and deaths, right? It's clear till here, right? If you had doubt here, just point it out here, because I'm trying to explain how do you get the population growth equation here. Okay, if you're confusion, please stop and let me know. I can repeat it again. So since, in a population, the number of births that can happen and the number of deaths that can happen is, uh, is fixed, can be a fixed number, right? You can have an estimate key, let's say in a year this this species, have, 10 births on an average or something like that, or 10 deaths on average. Okay. So since these are, relatively fixed for some populations, or you can have estimates, you can simply convert it to, you call a, new value. You can, together they can be combined into a new value, right? Let's call this value as intrinsic growth rate, or growth rate. Okay. So what does this say? It talks about basically the births and the deaths. If R is much more higher, so you say the population, births are much more higher and deaths very few, then R should be positive, right? And births are less, deaths are more, then the growth rate will be negative. Okay, so it can be simply rewritten as this equation as Rn, right? So you can say at n plus 1, the number of populations present can be Rn. Just they're just birth and deaths that are happening in this population. Okay, let's try to solve this. How to, what do we see when we do this? So let me just open an Excel sheet and then try to, show you how it can be done in Excel. Uh, so if you see here, let's say, okay, let's say we have time. Okay, time, it can be every 10 minutes, right? Time one, time stamp 1, time stamp 2, time stamp 3, time stamp 4. Okay, n is the number of individuals you have at that time. Let's say we're starting with a single cell bacterial cell, and n plus 1 is after one generation or one time period. Okay, so how to calculate this? So what is our formula? N plus 1 is equal to n into r. n times r. Okay. We are defining r here. R is basically, sorry, r, let's say we have an r of 2. So the growth rate of the population is 2. Okay. So we can simply write this equation as n, the number of individuals present in the previous generation, times the growth rate, right? If you multiply this, the number of individuals that you see in the next generation is 2. Okay. And then this will be your starting generation for the next uh, next cycle. So basically you can add dollar symbols for it not to change the cell. And now we'll just copy this formula across the cells. Let's say we are looking at 20 generation. After 20 generations, what happens? So yeah. So once I copy these cells, it will just copy the formulas. Let's say after 2 generations, the number of cells I have is 4 cells, 8 cells. After 4 generations, it's 16 cells, 32 cells, 64, 128, 356. Okay, if you plot this on a graph, so what do you see is, yes, I'm using a line plot. So what you see is, something called exponential growth, right? It's just increasing exponentially. It was, 2, 4, 8, 16, 32, 2 to the power. The exponent, the equation is 2 to the power here. So it's showing what you call an exponential, growing exponential. So you call it exponential growth. Okay, but do you guys think this happens consistently, or this is generally seen in nature? This exponential growth, basically, that means the population just keeps on increasing this much exponentially, especially. Opinions? Do you think this will happen or not? With that exponential growth, is it common, or can happen sometimes, cannot, or doesn't happen at all? Malthusian law. It happens. Uh, I'm sorry, I'm not aware of that law, but I don't think I'm able to recollect it as of now. But going by what you're saying, it happens. Uh, yeah, it happens to a little extent, but not in the, if you look it entirely, it will not happen, because, for it to happen, after a certain time, if you come back to the bacterial example, the bacteria will overgrow the amount of resources present in that area, in that plate that you're growing, right? So it has to stop. So basically it will stop. And then similarly that's true across life, or things that you see in nature. So eventually it will uh, stop growing exponentially. Okay, because the resources are limiting, right? So because when the resources get limiting, so you no longer have exponential growth. Okay, so then what you have is called, logistic growth, because once the resource starting to, limiting, the growth saturates at a point, because uh, the resources that are available can, support some some only few specific number of individuals, which we call carrying capacity. Okay, as more and more individuals get added, as it nears to the carrying capacity, the growth rates, decreases. Okay, and then the population is maintained at that specific level. Okay, if we do the same thing, try to plot with this formula n by k. So the population will grow initially, and then there has this exponential phase. Initially the phase is it's slower, but once it reaches this phase it's growing pretty fastly. But as it approaches this level, the number of you know individuals tends to stay constant across time, because that's the most number of individuals that can be supported by the system because of carrying capacity. So the carrying capacity can be food, it can be space for nesting, roosting, or mating, or there can be n number, but basically the carrying capacity in terms of any resource. Okay, so that is the difference between uh, exponential and logistic growth. So exponential just grows indefinitely, but that's not possible because resources are limiting, and then space is also a resource, which is the main limiting thing. Okay, so what we see is mostly logistic growths for most of the species, or in most cases. Okay, this is clear, right? Do you guys want me to do this and try and solve this example also for logistic growth, or are you just happy with these values in the graph, like what we did in Excel for exponential growth? If you want me to, I can do that. But if you are clear and then that's not necessary, I can stop there. Okay, then in that case I will move on because no one has said anything that is needed. So yeah, but in natural populations, there's this interesting thing, you know because each species is not individual on it itself, because there are different things that are affecting the species, and this species affect different other species in together. So there is this interesting theoretical model that Lotka and Volterra, they are two different persons came together to try and explain how two different species interact, how the populations of two different species interact in space and time. So one such example is prey predator interactions. So where as you generally know, prey and predator, as theory, they theorize that as the prey number increases, the predator slowly follows, because we know that more the number of prey, the more the number of predators are. And as the number of predator increases, more number of prey are killed, and then subsequently prey population drops. Since there is very less food, the predators population also drops. Since there are very few predators, and again the prey population increases, and so does the predator population, and then this thing goes in cycles. Or if you look at in time versus the number of individuals here, it just goes in peaks and troughs, peaks and valleys, you can say. And the predators closely follow prey, because the number of prey are huge in number compared to predators. We have larger graphs for prey rather than predators. Okay, so they have said Lotka Volterra equations predict that these cycles will happen, but does it really happen in nature? So what people has done was they found out this classic example from Canada, where there is this felid called Canadian lynx, and then there is this hare called snowshoe hare, which is represented in black and then white graphs here. So this animal specifically preferably preys on this, and then vice versa. So what happened was there used to be this fur trade where these animals were hunted. Both of these animals used to be hunted during those times, and then those records are number of individuals that were hunted or captured were meticulously recorded, and then someone used this data to try to plot them. And what they have found out was, the species indeed follows the cycles. So that is what we are seeing. As prey increases, predator is also increasing. As the predator increases, prey falls down because they are hunted like anything, and then if there is less prey, it just drops down, and then it just goes on oscillating. Okay, so yeah, this happens, but this is a very simplistic view of looking at two different species, because we know, because it's not just the predator that affects the species. There can be population, there can be hunting, human hunting, that might be happening. There can be diseases, there can be parasites, there might be multiple things. But this is a simplistic way of understanding how these two things move in space and time together, how one species affects different species. So this is for predator and prey. They can be simultaneously, can be looked at for different competing species, how two species compete with each other. So it's not exclusively for predator and prey. These equations are made for. Okay. Yeah. So that's all I have for now. Hope things were clear with this. If you have anything, just let me know so that I can clear them up again. So I have not written down the equations here because it's little complex. It might be little complex to understand them. So just referring to how the cycling happens. Uh, if you guys have any questions or clarification based on today's class or topics that were covered today, uh, do let me know so that I can cover them again if you have any. So okay, do let me know if there is anything that you want me to cover about, or revisit again, or the things that were discussed in the class if you see. No answer. So I will take it as an S and saying hope that it was clear. So in that case, I will end the presentation here. Okay. So yeah. So that's the end for today, I guess. So if you have anything more, I can wait for 2 3 minutes to help you clarify some questions from previous assignments or previous classes or discussions. Thank you for joining. I will be here for another 4 5 minutes. In the meantime, if you remember, if someone wants to ask, do let me know. If it's a no that you're not willing to ask, you just let me know so I can, yeah, we can call it a day for here. Okay, then in that case we'll stop here. Thank you everyone for joining.